Okay, very good evening all. Welcome to problem solving session number 10 of the course Mechanics of Material. So let's start the session for this week. Today, as usual, we'll see some problems from the topic that have been discussed in the class. So before diving into problem, let me quickly start with some of the concepts that we will need in order to solve the problems, concepts and formulas. So mainly in the last week, we would have seen something related to torsion, right? So torsion. Already we have seen a boundary value problem involving axial members and also flexural members, where we saw how to find bending moment, shear force, deflection, rotations, and all. And now this is the third class of problems where we see how to solve members that are subjected to torsion deformation. Say moment about its own longitudinal axis. Say suppose if this is axis x, moment about x we call as twisting moment or torsional moment. So this will cause a rotation twist in the members, right? So fine. First, we would have seen something called the torsion equation. So torsion of a closed wall section, thick wall or closed sections, especially the circular sections, which doesn't warp. So that's the first part. And the second part, we would have seen how to analyze for torsion with warping, right? So these are the two major topics. So first, we'll quickly see the torsion equation. That is, suppose if we have, so let me just take it. Yeah. Suppose if we have a shaft, solid circular shaft like this, and we are subjecting this to, say, there is a straight line. The assumption that we make here is that this straight line, after twisting, it say this is AB, some AB. Now this, after my twist, say it becomes like this. I am applying a twist here, right? Like this I am applying, so it is rotating. Okay, this straight line remains straight line, so that is the assumption. So it won't warp. Okay, so this is shear strain gamma, and now A moved to A dash, and this is the center of the section, and this angle, say this is some phi, and this is the radius, say rho. Now we say a dash, and I'm just throwing the quick derivation. A dash is nothing but rho times phi. The same a dash can be written using the radius. This is, say this is the length of the member, and this is the shear strain. So we can also write L gamma. So from this we will get the shear strain to be rho phi by L, right? So this is shear strain. Now if we assume the material moduli, the shear moduli to be G, so G will be equal to tau by gamma. So this implies when we substitute for gamma, so we will get gamma equal to tau by G. So tau equal to G phi by L by rho, or we say R. So okay, this rho is the radius of shaft. Okay, so this is the one part of the torsion equation. And suppose if you want to go with the force side, that is the applied moment, twisting moment is T. This is T. This T is equal to moment is nothing but force times the lever arm. What is the force? Force is nothing but stress times the area. The stress is the shearing stress, tau into dA is the total shearing stress, and lever arm is R. So this will give us we can substitute for R. Let me use R itself here for to maintain consistency, or here let me write rho. Okay, so tau we can substitute as integral tau rho. Tau is g phi rho square by L dA. So this implies g phi by L integral rho square dA. So what is integral rho square dA? This is nothing but the polar moment of inertia. Gj tau by L is T. Right, this tau, phi by L. This phi we call angle of twist. Okay, and T by J, again, if I want to extend this, we can write T by J equal to G phi by L. And from these two, we can connect the torsion equation, that is T by J equal to G phi by L equal to tau by rho. Okay, this is the torsion equation. Okay, so we'll quickly solve some problems based on this equation. Here, the assumption is main point to remember. The assumption is that these lines, these boxes after deformation, like if I have a box, square box here, after deformation, it remains square. Like there is no warping occurring. The box, what I meant is, if we have a shaft here, and if I suppose draw some lines on over the surface, after my twisting, these boxes will remain boxes. It won't cause curve linear deformation. It will remain straight. Only thing, it will become slant, right? So this we say the assumption that we follow. Okay, so let's solve some problems. So problem number one. So we are given with a given a hollow cylindrical steel shaft. Okay, the length of the steel shaft is 1.5 meters. The inner diameter is 40 mm and outer diameter is say 60 mm. We have to find what is the largest torque which can be applied if the shearing stress should not exceed 120 megapascal. Okay, this we need to find. And another value, what is the corresponding minimum value of minimum value of shearing stress. Okay, these two questions we need to solve, right? So how to solve? Let's begin. So di is given, d naught is given, t we need to find, yeah. So the t by j equal to tau by r, right? So this we can use, and we know the tau is given, the 120 megapascal, and rho is nothing but the radius of the shaft right? So the maximum, where the maximum shear stress will occur, it will occur at the surface, the outer surface. Where the minimum will occur at the center, right? Suppose if it's a hollow shaft, as given in this problem, the minimum is going to occur at the inner radius surface. Okay, right? Because from this expression we see it is directly proportional to the distance from the center. Okay, right. Now this implies we need to find T. So tau J by R, right? So this is what is tau 120. What is J? J is polar moment of inertia for a circle section. It's pi by 32 d power 4. Since it's a hollow, d outer power 4 minus d inner power 4, right? So this is equal to, maybe I'll write as it is, pi by 32. Mm, D outer is 60 power 4 minus 40 power 4 divided by radius, the outside surface, that is 60 by 2, which is 30. So this 4, 8, remaining pi by 8, 60 power 4 minus 40 power 4. Okay, let's use a calculator. 60 power 4 minus 40 power 4 into pi by 8. Okay, so 1, 2, 3, 4, 5, yeah, 4.084 into 10 power 6 Newton mm, right? Because everything was in Newton per mm square, mm per 4, everything. And this I can write 4.084 kilonewton meter. Okay, this is my T. This is the maximum value of torque which can be able to resist it without the shear stress exceeding the maximum limit given. Right. Next, what is the minimum value of shear stress? For solving B, that is minimum value of shearing stress. So mean now from this we can write, that is tau by r, tau by the radius is equal to, say, g theta by L, right? G theta, g phi. Let's be consistent. The derivation I have used rho for radius, but here r is better in the problem, so I've shifted the radius representation to capital R. Just make a note. So here, and this is theta is phi. Okay, so at the outer surface, tau max will be equal to R max equal to G will be same for a material and phi will be same, L will be same. And similarly, tau min by R min, minimum thing will be, okay, at a given section, my phi is same, G is same, L is same. So when I divide these two, I'll get tau max by R max is equal to tau min by R min, right? So this implies tau min equal to just R min by R max times tau max. Okay, so this is a direct relation we have. Now, minimum stress will be tau min is equal to, what is the minimum radius? 20 mm. And what is the maximum radius? 30 mm. Into what is the tau max? It's 120 megapascal. Okay. Given so 3 4 are. So 80 megapascal is the minimum. So we can able to get the shear stress variation, right? In the outer surface, it is 120 and it is reducing, it's changing to 80 at the inner surface. Fine. Okay. Let's move on to the next problem. Given now, it's little interesting. So whatever we have seen is one of the basic problem. Let's go on to a little more complicated problem. So problem number two, we are given with a series of shaft. Let me draw. So here there is a circle. This is a shaft, and this is again a circle, and this is another portion, and this is another cylindrical thing, and again cylindrical. Okay, and this is whatever is it at the center is the uh, shaft. So A, B, C, and D. Okay, given BC is a hollow shaft. BC is a hollow shaft. Uh, for BC, inner diameter is 90 mm, outer diameter is 120 mm. And for AB and CD, AB and CD are solid shaft. Okay, solid shaft. Diameter is say D, it's not given here. Diameter is D, both are of same diameter. Now, there is some external torque applied. At A, there is some torque, TA, in this direction, which is 6 kilonewton meter. And at B, there is a torque of 14 kilonewton meter. TB is 14 kilonewton meter. And at C, there is a torque applied in the opposite direction. So this is TC, this is given as 26 kilonewton meter, and at D there is another torque in the opposite direction. So TD equal to 6 kilonewton meter. Okay, so for those who joined just now, I'll just go through whatever I have been telling the last few minutes. I just started with the concept of torsion. Started with the torsion equation, the T by J equal to G theta G phi by L equal to tau by R. So T is the external torque applied. This is moment about its longitudinal axis, and J and just a cross-sectional area property, the moment, polar moment of inertia. G is a material property, and L is the sectional property again, the length of the shaft, and tau is the force, the shearing stress, right? The rho is the radius of the shaft. So using this, we just saw a problem where we found what is the value of torque and the minimum value of shearing stress. Okay. Now the current problem that we are dealing with is a series of shaft A, B, B, C, C, D, where BC is a hollow shaft given, and A, B, and C, D are solid shaft of diameter D. Now we have to find what is the maximum and minimum shearing stresses in shaft BC. So we need to find Tomax and Tomin, Tomax and Tomin in the shaft BC. Okay, that's first question. Second question, if the required diameter, okay, if the allowable shearing stress tau allowable is given as 65 megapascal, we need to find what is D. Okay, let's solve the problem. So first, we need to solve for the shaft BC, right? For that, we need to draw the free body diagram. So, drawing free body diagram is very important. Once if we can able to draw it accurately, easily we can solve the problem. Now, let's redraw. I am going to cut each of the sections A, B, B, C, and C D separately. So, say AB is here and BC is here and CD is here. Okay, so this is A, this is B, this is B and C and D. Now, at A, there is some external torque. So let's use this thumb rule, right, and thumb rule in order to represent the torque direction. So suppose if my torque, say, if this is my shaft and if my torque is applied like this, I'll keep my finger in the direction of this and my thumb will point this direction. Okay, this is my direction of torque. Or if I suppose if I do this, my thumb will point in this direction. So this is the direction of torque. So this is how we represent the torque direction using the right hand thumb rule. Just curl your fingers, the four fingers, along the direction of the torque, and the direction of the thumb that pointing is the direction of the torque. So I'm going to use that instead of drawing the arrow mark, the curly one. Let's find. So at A, it is going in this direction. So my thumb is going to point towards this, right? Double R. So this is TA. And at B, now Newton's third law, I have cutted the section at B. So every reaction there is equal, and for every action there is an opposite and equal reaction. Okay, so at A, my TA is pointing in this direction. So at B, my TB is going to point in this direction. Right. So this is again there will be a TA to maintain equilibrium. Now again, TA is here. So here TA is going to be like this. Okay. And in addition, there is a torque acting in this in BC direction. My thumb is pointing because of this arrow or torque. My thumb is pointing in the BC direction. So what's going to happen? There is another torque which is going to be added, which is TB, right? And to maintain equilibrium, there is another torque which is in the opposite direction, which will be TA plus TB, correct? And again, action and reaction. So this TATB is going to come here, right? This is TA plus TB. But in addition, there is another torque there, which is acting in the opposite direction, in this direction. This is PC given in the question. And finally, there is a torque which is in this direction, TD. It's also given. Now we can check this whether all our assumed direction are correct or not. Just substitute the values and we will see it is correct. So TA is 6, 6. So this is 6. and TA plus TB will be 20. So this the BC is subjected to a twisting moment of 20 kilonewton meters, right? And about CD, here C is in that direction, and A plus B is in this direction. So 26 minus 20. So the net direction will be this, just TC minus of TA plus TB. Okay, so this will be 26 minus 6 is 20. Okay, now TD, wait, 26 minus 20 is 6, nah, sorry. So 6 kilonewton meter. Now my TD is also 6, right? Both should be same. If it is not same, there is something wrong with whatever we are doing, right? Now we are interested in the member BC. Okay, so BC, what is the maximum and minimum shearing stress? So tau max, the T by J equal to tau by R. So tau max will be T by J into R max. So T is 20. We just saw TA plus TB is the torque which is acting in BC. J for BC will be hollow shaft. So pi by 32. DO power 4 is 120 power 4 minus 90 power 4 into R max will be 60. Correct. So this will be equal to, let's use the calculator, 20 into 10 power 6 into 60 into 32 divided by pi into 120 power 4 minus 90 power 4. Getting 86.2, 86.23 megapascal. Okay, tau max. Right. Now, if I want to find tau min, I can just substitute tau min equal to R min by R max into tau max. So this is equal to, what is the minimum? 90. R min or T min, both can be, this is 45 by 60 into 86.23. Just 3 sa 4 sa. This time 75. So 75 percentage of that. 0.75, which is 64.6. Okay, right. Now, how about subdivision B? We need to find what is the allowable stress in. No. We need to find the diameter of the shaft AB and CD if the allowable shearing stress in these shafts is 65 megapascal. Okay, in AB and CD. Let's do problem number subdivision B. So again, tau is given. So by T by J equal to tau by R. So this is equal to what is in AB? In AB, T is equal to how much? 6. And tau allowable is given in the question, which is 65 megapascal. And J, we know, it's unknown. It's a solid shaft, so fine. So let's substitute 6 into 10 power 6 divided by pi by 32 into d power 4 equal to 65 divided by d by 2. Okay. So this will become d cube equal to, this equal to, d cube will be 6 into 10 to the power 6 into 32 by pi into 65 into 2. Correct? Yes. So let's find it out. 6 into 10 to the power 6 into 32 divided by pi into 65. 2s are 130. Cube root. Cube root power 3. No, power 1 by 3. How to negate this? Oh, oh. Yeah. Power. Oh. Into 1. 0. No, no. I have to do, sorry. 6 into 10 to the power 6. We should have utmost concentration while doing this. 32 divided by pi into 130. Okay, this to the power 1 by 3. The cube root. 77.76 mm. This is as per shaft AB. Okay. And now I think we are done, right? So this is the diameter. Okay. Now moving on, let's move to the next problem. One of the problems similar, very similar to your assignment. Problem number 3. Given a shaft, step shaft, like here AB is there and A, B, B, C and C, D and D. Okay, so this is my A and B is at 100 mm. B, C, D, E. This is 100. This is 300 mm length, 400 mm length, 600 mm length. There is a twisting moment, external torque applied. So this is in this direction, and here it is in this direction. Okay, so this is TD and this is TB. Okay, and the diameter also given. This diameter is given by 20 mm and this diameter is given by 40 mm. And this value of TB is 200 Newton meters and value of TD is 1000 Newton meter. This is steel, so Young's modulus will be uh, 200 gigapascal and mu Poisson ratio will be 1 by 3. Now what we need to find? We need to find the following: magnitude of torque, magnitude of torque at E, TE equal to watt, and magnitude of angle of twist. This phi at A equal to watt in terms of 10 to the power minus 3 radians, and phi C equal to what in terms of 10 to the power minus 3 radians, and phi D equal to what in terms of 10 to the power minus 3 radians. Okay, so these are this is the question that we need to solve for. Right. So now, let's first just draw the free body. So in the free body, I'm going to segment them into A, B, B, C, C, D, and D, so that it is easy. That's how we need to f- solve, because we have been asked question to find twist at A, twist at C, and D. Right. So also there is a torque, external torque applied there. So let's cut it out and see. First, AB, this is my AB. In AB, what's happening? There is no external torque, right? You can ask, no, no, at B there is a torque, right? Where is the torque went? You can ask. But I am drawing the points which are just before that B point. So there is, it's free of any external loading. Okay, so there is no torque. Now, how about BC? BC, yeah, of course, there is an external torque here. This is TB, and this will be TB. Okay, for equal and opposite. This will be uh, okay. Yeah, let's move on. I thought to write the names. This is A, B, and C. How about for BC? No, BC done. CD and D. Okay, C, there is a torque at that. So this will be equilibrated, TB. And at here, there is again, this will be equilibrated, but this is TB, and this will be, let's draw it neatly. Okay, this is TB, and Here there is TB acting, but in addition to TB, there is some external load which is in this direction. Just TD. Okay. So at E, what will be my net torque? My net torque, if I assume TD to be mm, positive, so this will be TD minus TB. Okay, right. Now, if we substitute the values, this is 200 and this is 1000. So this is totally, it will be 1000 in this direction and 200 in this direction. So the net will be 1000 minus 200, which is 800. And here similarly, this is 800. Okay. Now the first question we need to solve for is done. That is the torque, magnitude of torque at E is nothing but 800. Okay. So TE will be 800 Newton meters, right? Yeah, in this direction. Okay. Here, if you want to denote this direction. Second question, angle of twist. Finding angle of twist. Now, if I want to find the twist at say A, so the twist at A will be equal to what? Twist at A will be equal to twist at B, right? This AB portion, and then twist at AB portion, twist at BC portion, twist at CD portion, and twist at DE portion. Right. So this is nothing but because when we twist this, the twist at A will be the summation of all the twists which are occurring, right? Because it just we can visualize it, right? When we rotate this, in the case of deflections also in beam, same thing we would have seen. If suppose if there is a cantilever and this deflection, this will be greater than this, right? Although it is not straightly linear, but this will be greater than this. Similarly, here also the twist will be the summation of all the twists which are happening before. So, what is the formula for angle of twist from the relation? This phi uh, T by J equal to G phi by L. So phi will be TL by GJ. This will be T by GJ of AB and so on. This, what is T of AB? 0. 0 plus what is T of BC? BC is positive 200. Length of BC 200 Newton meters, right? Yeah. Length of BC is 300 mm. by G is same for everyone. So let's take it outside, and J of AB or BC is 20 mm. So pi by 32 into 20 power 4. Okay. This plus what is for CD, T of CD is 200. This is CD, 200, and length of CD 400 by pi by 32 into for CD it is 40 mm, 40 per 4. Okay, plus how about DE? It is minus 800, right? Negative 800. Length 600 pi by 32 into 40 per 4. This is equal to, this pi by 32 is also common. This the whole times that G will be there, no? So 32 pi by G is 200 gigapascal, right? 200 into 10 power 3 megapascal I'm converting. Okay. Pi will be in denominator. This is 1 by G. Remaining things we can just simplify. Let's do with the calculator. 200 into 300 divided by 20 power 4, 0.375 plus 200 into 400 by 40 power 4. Second, 200 into 400 divided by 40 power 4. 0.03125 minus 800 into 600 divided by 40 power 4. 1875. So this 0.375 plus 0.03125 minus 0.1875 times 32 divided by 200, 123 into pi. Okay, so 1.114 into 10 to the power minus 5. We want in terms of 10 power minus 3 radians into 10 to the power 3. So 0.0111, right, into 10 to the power minus 3 radians. Okay. This is for twist in AB or in A. Next question about angle of twist in C and D. In C, how this will be? Yeah, here it is. So at C, if we need to find, we need to add two components. That is the CD thing and the DE thing, right? So phi C will be equal to again TL by GJ of CD TL by GJ of DE. Again, since we have already computed this, CD and DE, just 32 by 200 into 10 to the power 3 into pi 0.03125 minus 0.1875. This will be just calculations 0.03125 minus 0.1875. This into 32 by pi into 200 123. Okay, this into 10 to the power 3. We are interested in only the magnitude, so I'm ignoring the sign. 6 into 10 to the power minus 3 radians. Okay. Similarly, in D, so only the portion DE will be there, right? TL by GJ of DE. This is equal to this 32 by 10 power 3 into pi into minus 0.1875. 0.1875 into 32 by 200 123 into pi into 1000. So again, the magnitude will be 0.0095. Okay, that's it. Fine. Yeah. Let's move on to the next problem. A problem involving statically indeterminate structures. This is problem number 4, right? Yeah, problem number 4. So we have been given with a circular shaft AB uh, 250 long. Okay, so this is a shaft, and here also it is fixed inside. Let me show it here. And there are two portions. Here it is hollow. A cavity has been drilled. This is the cavity. Okay. Okay, this is again fixed, but I'm just showing the internal side. Now, AB, the total length is 250 mm. This is A, this is B, this is C. The total length is 250 mm, and this is 125, that is 125. So it is center, and there is some external torque applied in this direction. This is 122 Newton meters. Okay. And the dimensions are also given. The original dimension is diameter is 22 mm dia. Okay, but the cavity diameter is 16 mm cavity. Okay, diameter, and it is fixed support at both the ends. Okay, these are all given. What we need to find is determine the torque exerted on the shaft by each of the support. That is torque in support A and torque in support B equal to what? Okay, that's it. So this is the question. Now we need to solve. This is the indeterminate problem. Means both ends are fixed. So we need compatibility condition also to solve, not just equilibrium condition. Now let's write. Maybe we will draw the free body. So when I cut the free body at A, C alone, just left of C, there is, say, assume there is some TA reaction. Okay, TA. So just left of C, this TA will be there as it is in the opposite direction. Now from C, CB, this is A, C, C, B. Now this will be in this direction, TA will be there as it is, but there is some external torque in this direction, right? This is 122. So now T D will be, let's take, this is the TD direction. Okay. That is TA plus TD will be equal to 122. Or this TA minus 122 will be equal to TD. So TA plus TD will be equal to 122. Okay, this is equation, but we cannot solve just using this equilibrium equation alone. It's an indeterminate structure. We need one more equation in order to solve so that we will be able to uh, compute the unknowns. Now, what is that one more equation? We need to play with the compatibility. Here, there is something related to angle of twist. Now, both the ends are fixed. We can say the net angle of twist or the total angle of twist of shaft, this AB, total angle of twist of shaft AB will be what? Will be 0, right? Because the both ends are fixed, even though there may be a twist happening because of the torque applied at C. One portion will be rotating in one direction, another will be rotating in the opposite direction. So the net rotation, the twist will be 0. Right? So that's the compatibility. So the phi, which is phi, say 1 plus phi 2 will be 0. Let's substitute. Let's just phi T by J equal to G phi by L. So phi will be TL by Gj. So TL by Gj of 1 plus TL by Gj of 2 will be 0. Now let's substitute TA, L of AB. So 125, 125, so it will get cancelled. G, same material, it will get cancelled, equal to 0. Mm, J1 will be, it's a solid for 1, that is A, C and CB, okay? Mm, what is J of AC? Pi by 32. What is the diameter? 22. D power 4. Plus, what is T here? And it's a negative, so negative of TD, right? TD by these cancel in pi by 32, and here it's hollow, so 22 minus 16. So this also gone. So TA by 22 power 4, TD by 22 power 4 minus 16 power 4. This equal to TA will be, what is this, 22 power 4 by 22 power 4 minus 16 power 4. Okay, this will be 1.388 times TD. Okay, so let's substitute back in equation, say 1 implies therefore TD will be this plus 1 reciprocal of this times 122. 51.08 Newton meters. So TA will be into 1.388. This is 70.89, just 90. Okay, right. That's it. Okay, we are done. Okay, this is not D, it is B, no? From where I got D, this is B, this is B, this is B. There's no D in this. Done? Yeah. Let's move on to the next problem. Problem number 5. Yeah, here it is. We are given with a horizontal shaft, which is attached to base D. So this is A, B, and again there is a hole has been drilled into portion CD. CD, this fixed thing is D, and there is some hole which is drilled inside. Okay. Right, so this diameter is 44. This is 44 mm. The total diameter is 60 mm. This is 60 mm. Okay, the cavity, the hole is 45. Now we need to note down the lengths. Lengths are given as from A, A to B, it is zero point 0.4 meters, 400 mm. From B to C and from C to D, it is 200 mm, zero point 0.2 meters, this is zero point 0.6 meters. Okay, the magnitude of torque also given. This torque magnitude is 250 Newton meters, and this diameter is also given. Before that, let me finish up this 2000 Newton meters, and this AB portion diameter is 30 mm. Okay, Now, what we need to do, we need to find the material. By the way, the material is property is given as 77 gigapascal. Okay, we need to find the angle of twist at A equal to what? Right, angle of twist at A. Okay, this is what we need to find. Let's solve. Now, angle of twist at A will be given by angle of twist in the portion DC plus angle of twist in the portion CB plus angle of twist in the portion BA. Okay, all these three will be adding up, right? Now, and for each of the thing, we need to know the torque first of all. So, as usual, let's draw the free body first. This is portion CD, BC, and AB. Here it is 250. So here also will be 250, right? This is AB done, and BC 250 is here, and in addition to that, there is some 2000 in this direction itself, and this is 250. So there will be 2250. 2250. And here it is again 2250, and there is no other thing, so 2250. Okay, AB, BC, CD. Okay, these are the things. Mm. Now, yeah, let's solve. For portion DC, uh, we need J of DC will be pi by 32 into 60 power 4 minus 44 power 4. And J of BC will be pi by 32, 60 power 4. J of AB will be pi by 32 into 30 power 4. Okay, right, and length of DC will be 600 mm. Length of BC will be 200 mm, and length of BAB will be 400 mm. Right, now this will help us to solve. So A will be, what is that? TL by GJ. T is there, so minus 2250 into 600. This is Newton meters only, right? Yeah, Newton meters. So into 10 power 3, I should write. Oh, okay. Somewhere I think I missed 10 power 3. Then in this sum, this is Newton meters. Okay. So in the calculation, we have used mm. So this is 10 power 3 will come. So whatever the answer, this multiply by 10 power 3 will come. Just make a note. 1, 2, 3, 11.1 into 10 power minus 3. Okay. For mm. And similarly, this will be 1, 2, 3. 7.96 into 10 power minus 3. And this will be 1, 2, 3. 9.55 into 10 power minus. Okay, this is a silly mistake. Torque is in Newton meters, but whatever units that we are using is in mm. So we should have converted this right into 10 power 3. Okay, just make a note of it. Right. In this sum, let's come back to this sum. Phi A will be TL by GJ. L is given T this into 10 power 3. Na? Here only I catch that. This divided by GJ. G is 77. No? 77 into 10 to the power 3. J is as given. Okay. So this is phi DC, phi CB will be, phi CB will be minus 2000 into 10 power 3 into 200 length by 77 into 10 power 3 into pi by 32 into 60 power 4. Okay. And phi AB will be minus 250 into 10 to the power 3 into 400 divided by 77 into 10 power 3 into by 32 into 30 power 4. Okay. Now just solve. 2250 into 600 divided by 60 power 4 minus 44 power 4. This is one term, and this plus 2000 into 200 divided by 60 power 4. This is second term plus 250 into 400 divided by this 80. Yeah? Sometimes I'm finding difficult to read my own handwriting. So this is 30 into 30 power 4. Okay, so I've added all, taken something common, that is into 10 power 3 divided by 77 into again 10 power 3 into pi. Okay, this into 32. So I'm getting ultimately 0.0398. I'm getting. There may be an error in the computation. Just check it. So phi A, when we add everything, it is minus 0.0. I should get 0.0403 radians. Now, when we convert this into degree into 180 by pi, we will get 2.31 degrees. Okay, fine. There may be only calculation error, nothing else, or while I substitute. Okay, that's it. Now, what's next? So this is problem number 5. Next, we'll see a problem similar to your assignment problem number 3. Problem number 6 here. So there is a composite wire, made of two materials, solid brass core. This is solid brass, uh, with the diameter 10 mm, and this is copper casing. This diameter is 20 mm. This diameter is 10 mm. And it's subjected to uniform torque of 500 Newton meter. The material property is given. By the way, again, when we are saying material property, I again recognize the mistake which I have done before. In the question, we had been given with Young's modulus, but here we needed shear modulus, right? In problem number 2, I guess 2 or 3. Yeah, here, right? This is E, but I think I have used directly the value. This is wrong again. Okay, these are all mistakes that everyone makes. So, plus, just please make a note. This will be wrong. So instead of this, G will come. Okay, not E. How to find that? There is a relation between the shear modulus and the Young's modulus. E equal to 2G into 1 plus nu. So from this G will be E by 2 into 1 plus mu. Okay, so careful. Okay, this, so again, this value and this value. Okay, yeah, let's do this. This is 40 gigapascal, and copper will be 45 gigapascal. Okay, we need to find few things. First, we need to find maximum shear stress in brass and maximum shear stress in copper, angle of twist per unit length. Okay, so these three things we need to find. Let's solve. Now, what will be the equilibrium equation. The total torque applied is 500 Newton meter. So the equilibrium equation will be the total torque will be equal to this torque will be going to both the materials, right? T brass plus T copper. That is T brass plus T copper will be 500. And what is again, this is not sufficient. We need one more. What is that one more? What is the one more equation which we need to solve this problem? Hmm? So here, like when we apply this torque of T, the twist will be same in both the materials, right? So the angle of twist in copper will be angle of twist in brass. So this is the important equation which will help us. So this will be equal to TL by GJ of copper will be equal to TL by GJ of brass. This will be equal to T copper. Length is same, so length we can cut. G copper and J copper here. J copper equal to again T brass, G brass, and J brass. So this is equal to T copper will be what is G copper? 45 by 40 times uh, J copper by J brass. So pi by 32, pi by 32 will go. J copper will be, it's a hollow. So 20 power 4 minus 10 power 4. 20 power 4 minus 10 power 4. And this is only 10 power 4 times T brass. Right? So this will be T copper is equal to 20 power 4 minus 10 power 4 divided by 10 power 4. This is 15. 5 8s are 5 9s are into 9 by 8 into 9 by 8. 16.875 times TBR. Okay. So substitute there. So T copper 17.875 TBR will be 500. So TBR will be 500 reciprocal of 29.63 Newton meters. Okay. And T copper will be this times or this minus 500. Let's this time 16.87. What? Mm, what happened? The brass is 500 divided by 17.875. This is 27.97 Newton meters. So this will be times 16.875. 472.0 3 Newton meters. Okay, that's it. What else? Yeah, angle. Okay. Question is maximum shear stress, right? So shear stress will be T by J equal to tau by R. So tau max will be T by T R max by J. So in brass, tau max in brass will be T brass. What is the radius, maximum radius of brass? 5 mm. 5 divided by J is 5 by 32 into solid, na? 5 power 4. T brass will be 27.97 into 10 power 3. Careful, only one time you will make mistake. Other repeatedly we should not. So 10 power 3 times 5 is in mm divided by pi by 32 times 5 power 4. All are in Newton or mm square. So this will give 27.97 times 1000 times 5 times 32 divided by pi times 5 power 4. Okay, so 2279.2 megapascal. Quite high. Let me just check once. $27.97 into 5,000 into 32 divided by 5 times 5 power 4. Okay. How about for copper? Tomax in copper will be T copper times radius max will be 10 divided by pi by 32 into 10 power 4 minus 5 power 4. Okay, so this will be the copper 472.03 10 power 3 into 10 into 32 by pi into 10 power 4 minus 5 power 4. This is equal to 472.03 into 1000 into 320 divided by 5 into 10 to the power 4 minus 5 to the power 4. Okay, 5128 point. This is quite high. It's because maybe the values which I have taken is not practical. Okay, so fine. Right, so this is how we compute the shear stress. And for subdivision C, angle of twist per unit length in radians per meter. Angle of twist per unit length is given as phi equal to TL by GJ. So T by L equal to T by GJ. Both will be same, the copper or the brass. Let's go with the brass, 27.97. 7.97 into 10 to the power 3 divided by brass thing is 40 pi by 32 into this is D is 10 power 4, right? 10 power 4. Okay, so this will be 27,970 into 32 divided by 40, 123 into pi into 10 to the power 4. Okay, this value we are getting is 7.1225 into 10 to the power minus 4 radian per mm, right? But we want in meters, so and into 10 power minus 3 also should be there. 71. I want to write finally in terms of 10 power minus 3 radians per meter. Okay, so I'll just multiply by 10 power 3. This I can write as 71.225 into 10 power minus 1, or I'll write 0.71225 to 10 into 10 to the power minus 4. So this will give us 10 to the power minus 3 radian per mm. This further 1, 2, 3, 712.25 to 10 power minus 3 radian per meter. Okay, that's it. Be careful based on whatever they are asking. Right, that's it. And yeah, this actually completes problem. Yeah, we have one more uh, to see. That is, we'll see one related to a thin wall sections with warping. Problem number, this is related to thin wall sections with warping. Okay. So here there will be change in the formula that because we cannot use that formula. Say suppose if we have a thin wall section, and if this is our axis x and y and CG, and if you are taking some element here, say this is ds, and the thickness of this is t. Okay, right now what is torque? Torque will be integral of force into distance. Force will be stress times area. Area will be thickness times the length. Right? This times the distance will be the lever arm. This is the tangent from the center. This should be normal. This is R. Okay. Now this integral ds into R is nothing but area of this triangle. right? This is say base ds, height is a perpendicular distance which is r. So area of this triangle will be half into ds base into height. So dsr will be 2 times area. Okay, so this substituting it here, t will be equal to 2 times. The tau t is constant, tau t. So rest of the thing, uh, ds into r. dsr we just saw that is the area of triangle. The integration of the entire thing will give us 2 times the area enclosed. Okay, area enclosed. Now the formula for shear stress we need is tau will be T by 2TA. Okay, this is the formula for shear stress in case of thin wall sections with warping. And similarly, we can able to find the formula for angle of twist using energy concept or other derivations, which is as given in the question in the lectures. I am not going to derive a shortage of time. This will be directly TL by 4 mu A square integral ds by t. Okay, right. So let's take a problem and let's see how to solve this finally. Problem number 7, right? Yeah. Given a 6 kilonewton meter torque is applied to a thin walled hollow shaft made of material with G is equal to 70 gigapascal. We need to find few things. First, shear stress at any point in the cross section dash. Next, we need to find angle of twist per unit length of shaft in terms of 10 to the power minus a radian per meter. Finally, suppose if the shaft angle of this same question, but if with longitudinal slit, okay, same question. Only thing longitudinal slit is extra, right? Let's solve the problem. Now, as I said before, just now we saw the shear stress formula for case of thin walled sections will be tau will be T divided by 2T area enclosed. So this T is 6 kilonewton meter, 2 times thickness. Is it given in the question? Yeah, it's given in the question. I forgot to note. This is given as 50 mm and this thickness is 10 mm. Okay, so this is 10. What is the area enclosed? Is pi into, sorry, r square, 50 square. Okay, radius square. This is the area enclosed. The mean, okay, this is not here, mean diameter, so radius. Okay, so just substitute 6 into 10 to the power 6 divided by 20 into pi into 50 into 50. So it is 38.2 megapascal. Okay. Next is angle of twist. Angle of twist, as we saw, phi by L will be T by 4 mu. Mu is nothing but G a square integral closed integral of ds by t. Right. So this will be t is 6 into 10 power 6 by 4 into 70 into 10 power 3 into 50 into 50 square in pi into 50 square, the whole square. What is closed integral ds by t? Integral ds is the pi into d, right? The circumference, pi into d. So pi into d is 100 or 100 by thickness is 10. It's 10 pi. Okay. This times 10 pi. So this will give us 6 into 10 to the power 6 into 10 into pi divided by 280 into 1000 into pi into 50 power 4. Okay. All these were in mm. So 1.0913 10 power minus 5 radian per mm, but we want in terms of radian per meters. Zero point 0.010912, okay, into 10 to the power 2, same, 10 to minus 3 radian per mm. This again 1, 2, 1, 2, 3, 10.9 into 10 power minus 3 radian per meters. Okay, fine. Now, final question. If suppose if we have a longitudinal slit, then for this case, with slit, the formula is that phi by L is 3T by G into that pi into dm, that is the integral, closed integral ds t cube. Okay, this is direct formula, so you can substitute here and get the value appropriate. Fine. Right. So I think that's it for the day. We come to the end of the section. I'll just quickly go through the problem. So we have seen how to solve problems subjected to members subjected to twisting moments, and we saw like how to find the angle of twist, share maximum minimum shearing stresses in the case of various problems, right? Mainly we saw how to find the free body, the twisting moments at individual sections, and yeah, finally we saw related to thin wall sections with warping. Okay, right. So with this, I'll stop here. Uh, Thank you very much for listening. And yeah, we'll see you again in the next week. Thank you. Bye.